Today I am going to present how to derive the expression for determination of deflection by unit load method. Consider the body shown in figure 1. So this is figure 1. This is the body in which subjected to the forces P1, P2, P3, P4, Pn applied at 1, 2, 3, 4 and gradually. So these are the points 1, 2, 3, 4 and n, and the force P1, P2, P3, P4, Pn applied at the point 1, 2, 3, 4 and gradually. The forces are applied here gradually. Let the displacement under the load points be delta 1, delta 2, delta 3, delta 4, delta n, and at point C be delta. So this is the deflection at point 1, delta 1, and this is the deflection at point 2, delta 2, and this is the deflection at point 3, delta 3, and this is the deflection at point 4, delta 4, and this is the deflection at point n, delta n. These are the deflection due to the applied force P1, P2, P3, P4, Pn gradually. And this is the point C. So here the deflection is your delta. So at the point C, the deflection is your delta. And in this body, so due to the system of the external forces P1, P2, P3, P4, Pn, the stresses produced in the element is your sigma. The stresses due to the external force produced is your sigma. The stress produced in the element is your sigma, and the strain in the element is equal to epsilon. Then you know from the strain energy method, what is the strain energy stored in the element? What is the strain energy stored? So because this is the stress is your sigma, epsilon, this is the strain. So what is the strain energy stored in the body? So this is your equal to from the strain energy method. So the strain energy stored is your equal to integration of half stress into strain into dV, the change in volume. Then due to the action of the external applied forces, what is the external work done on the body? Because this is the force and this is the displacement at point 1, and this is the force at 2, and this is the displacement at 2. This is the force at 3, this is the displacement at 3. This is the force at 4, and this is the displacement at 4. And this is the force at n, and this is the displacement at n. So you have to find out what is the external work done due to the external forces acting on the body. So you know that is when the forces are acting gradually, what is the external work done? So this is your equal to half into P into delta. But due to the action of the number of forces P1, P2, P3, P4, Pn, so what is the external work done due to these forces? So the external work done due to forces is equal to half delta 1 P1 plus half delta 2 P2 plus half delta 3 P3 plus half delta n Pn. So this is the sigma is the stresses in the element, and epsilon is the strain in the element. So you know the external work done is equal to the strain energy stored. That is equal to the internal work done. The external work done is equal to the strain energy stored. So half delta 1 P1 plus half delta 2 P2 plus half delta 3 P3 plus half delta n Pn is equal to integration of half sigma epsilon dB. So this is your equation 1. Now you are clear that due to the action of these forces, this is the displacement takes place. The displacement at 1, 2, 3, 4, n is your delta 1, delta 2, delta 3, delta 4, and delta n. And at the point C, the displacement is your delta. So the strain energy stored that you can find out. So what is the stresses in the element and what is the strain in the element? So you know the stresses produced in the element is your sigma, and the strain in the element is your equal to epsilon. The strain energy stored is your equal to the integration of half stress into strain into the change in volume. Then you know the external work done due to the forces is equal to half delta 1 P1 plus half delta 2 P2 plus half delta 3 P3 plus half delta n Pn. And the external work done due to the forces is equal to the strain energy stored in the body. So this is the half delta 1 P1 plus half delta 2 P2 plus half delta 3 P3 plus half delta n Pn is equal to integration of half stress into strain into the change in volume. This is your equation 1. Then in next case, what you have to do, only have to apply the unit force at the point C, and due to this force, what is the displacement takes place? Due to this force, what is the displacement takes place at the point 1, 2, 3, 4 and n? That you have to find out. And at C, what is the displacement takes place? I mean, so what is the external force you are given, that you have to remove? Only you have to apply the unit force at the point C. Due to 1 kilonewton unit force, what is the displacement takes place at 1, 2, 3, 4 n and at C? So the displacement at C is equal to, this is your the lowercase delta. This is uppercase delta. This one is your uppercase delta, and this is lowercase delta. The displacement at C is your lowercase delta, and at 1 the displacement is your delta 1, and at 2 the displacement is delta 2, and at 3 the displacement is delta 3, and at 4 the displacement delta 4, and at 5 the displacement is delta n. This is the displacement takes place due to the unit force. Now consider the same body subjected to a unit load applied gradually. This load also you have to apply gradually. At C, when it is free of system of P forces, as shown in figure 2. Let the displacement at 1, 2, 3, 4 and be lowercase delta 1, lowercase delta 2, lowercase delta 3, lowercase delta 4 and lowercase delta n, and at point C be lowercase delta. So due to this unit force, so what is the stress produced in the element? So that you have to take sigma dash. And what is the strain produced in the element? So this is your epsilon dash. The strain produced in the element is your epsilon dash, and the stress produced in the element is your sigma dash. So this is the stress and this is the strain due to the unit force applied at the point C. Then what is the external work done due to the unit force? Because this is the unit force, and due to this unit force, what is the deflection at C? This is your the lowercase delta. This is lowercase delta. So what is the external work done due to the unit force and this delta? So this is equal to half into 1 into delta. The external work done is equal to half into 1 into delta. What is the internal work done due to the stresses produced in the element due to unit force 1 kilonewton? So the stresses produced in the element is your sigma dash, and the strain is your epsilon dash. So what is the strain energy stored in the body? Or that is also called the internal work done. So this is your equal to half integration of half sigma dash, epsilon dash, and the change in volume. But you know, the external work done is equal to the internal work done. And you will equate these two. So half into 1 into delta, lowercase delta, is equal to integration of half sigma dash, epsilon dash, and the change in volume. So take this is your equation 2. So this is the external work done is equal to internal work done due to the unit force. Due to unit force, so this is the external work done, and due to unit force, this is the internal work done, or this is equal to the strain energy stored in the body. The external work done is equal to the internal work done, and this is equal to half into 1 into delta is equal to integration of half sigma dash, epsilon dash into the change in volume. This is equation 2. Then what you have to do now? If P system of forces applied to the body as shown in figure 3. So this the 1 kilonewton load, so this will remain at point C. Then what you have to do? You have to apply the P system of forces at 1, 2, 3, 4 n. You have to apply the system of P forces at 1, 2, 3, 4 n. Now if P system of forces is applied to the body as shown in figure 3, so this is because this force, the unit force is already present at the C, and due to this force, this is the deflection takes place. The lowercase delta 1, delta 2, delta 3, delta 4, delta n at 1, 2, 3, 4, n, and at the C point, this is the delta, the deflection. So this is your already due to this unit force, so this is the deflection. Then what you have to do? Then you have to apply the P system of forces at 1, 2, 3, 4, n gradually. Then you have to apply the P system of forces, that is P1, P2, P3, P4, and Pn at 1, 2, 3, 4, n gradually. Then due to this force, this is the deflection at 1, 2, 3, 4, and n. So delta 1, uppercase delta 1, delta 2, delta 3, delta 4, and delta n. Due to the P system of forces, this is the deflection takes place. Already this force is acting, and you have to apply the P system of forces at the point 1, 2, 3, 4, n gradually. Now, if P system of forces is applied to the body as shown in figure 3, so what is the external work done? After application of the P system of forces, so what is the external work done? What is the external work done due to the P system of forces? Half delta 1 P1 plus half delta 2 P2 plus half delta 3 P3 plus half delta n Pn. So this is the work done due to these forces P1, P2, P3, P4, and Pn. But this force, the unit forces are already acting on the body. These forces are already acting on the body. So what is the work done due to this force? This is already present in the body. So what is the work done due to this force? 1 into delta. Because this force is already acting on the body. So you have to take work done due to this unit force is equal to 1 into delta. Plus 1 into delta. So what is the total external work done due to the external forces? Due to the external forces and due to the unit force, what is the total external work done? Half P1 delta 1, half P2 delta 2, plus half P3 delta 3, plus half P4 delta 4, plus half Pn delta n, plus 1 into delta. Because this load is already present on the structure or on a body. Since unit load is already acting. Then what is the internal work done? What is the internal work done? Because this is due to the external forces. This is the internal work done or the strain energy due to the external forces. Integration of half sigma epsilon and dB plus, and this strain energy or the internal work done. So this is due to the unit force. This is the internal work done or the strain energy due to the unit force. So integration of sigma dash, because this is already present, this unit force is already acting on the body. What is the strain energy due to this unit force? So integration of sigma dash, epsilon, and dB. Here you have to take, this is the strain, you have to take epsilon, because after application of this force, so what is the strain? What is the strain that you have to consider? But the stress is remain same. So for this unit force, what is the stress is acting on the body? That is your sigma dash, and the strain is this one epsilon. After application of system of forces P1, P2, P3, P4, and Pn. So this is the internal work done or the strain energy stored. This is equal to integration of half sigma epsilon dB plus integration of sigma dash epsilon dB. Since the stress sigma dash is acting throughout the deformation, then what is the internal work done is equal to external work done. So you know this is the external work done. Half delta 1 P1 plus half delta 2 P2 plus half delta 3 P3 plus half delta n Pn plus 1 delta is equal to the internal work done is equal to integration of half sigma epsilon dB plus integration of sigma dash epsilon dB. So this is take equation 3. But you know from the equation 1, this is when only the external forces P1, P2, P3, P4 and Pn is acting on a body. So what is the external work done and strain energy relation? So this is the relation. Half delta 1 P1 plus half delta 2 P2 plus half delta 3 P3 plus half delta and Pn is equal to integration of half sigma epsilon dB. This is equation 1. And this is you got equation 3. So subtracting equation 1 from equation 3. So you have to subtract equation 1 from the equation 3. Then you will get 1 into delta is equal to integration of sigma dash epsilon dB. Then delta is equal to integration of sigma dash epsilon dB. So this is the expression for deflection. Using this formula, you will find out what is the deflection at a point using the unit load method. Using unit load method, by unit load method, you can find out what is the deflection at a point using this formula. Delta is equal to integration of sigma dash epsilon dB, where delta is equal to deflection at point where the unit load is applied and is measured in the direction of the unit load. Where you want to find out the deflection, so at that point you have to apply the unit load, then you can find out what is the deflection at the point using the unit load method. So that is the delta is equal to deflection at point where the unit load is applied and is measured in the direction of unit load. And the sigma dash is the stress in the element due to unit load. And epsilon is equal to the strain in the element due to a given load system. So this is the relation. So using this relation, you can find out deflection at a point by unit load method. Delta is equal to integration of sigma dash epsilon into dB. Then coming to how we will apply the unit load method to beam deflection. Here we will discuss how we will apply the unit load method to beam deflection. I will find out the deflection of a beam using the unit load method. These are the external forces. The external forces acting on the beam P1, P2, P3, P4. So this is simply supported beam, and this is considered the simply supported beam shown in figure and subjected to the system of P forces. So this is simply supported beam and subjected to the system of forces P1, P2, P3 and P4. These are the forces acting on the simply supported beam. Let the forces P1, P2, P3, P4 applied at 1, 2, 3, 4 respectively. So what is the stress produced in the element? The stress produced in the element is equal to sigma. This is a section. You have to take an element whose length is your dx and the cross-sectional area is equal to dA. And this is the stress is acting on the element. The stress acting on the element is your sigma. And this is at a distance y from the neutral axis. So this is the axis. This is the axis at a distance y from the neutral axis. Stress produced in the element is equal to sigma. Then what is the stress in the element at a distance y from the neutral axis? You know from the theory of pure bending. So what is the theory of pure bending formula? M by I is equal to sigma by y is equal to E by R. This is the theory of pure bending formula. So from that relation, you can find out what is the stress produced in the element. At a distance y, what is the stress produced in the element? So sigma is equal to M by I into y. So from the theory of pure bending, you know sigma is equal to M by I is equal to sigma by y. So sigma is equal to M by I into y, where M is the bending moment at the section. The strain in the element due to given system of forces, that also you can find out. The strain is equal to the stress by modulus of elasticity. So you know the stress is equal to M by I into y. So strain is equal to M by EI into y. So this is the stress and strain due to the system of forces P1, P2, P3, P4 acting on a simply supported beam. Due to these forces, what is the stress and what is the strain produced in the element, that is your sigma and epsilon, and the sigma is equal to M by I into y and the epsilon, the strain is equal to m by ei into y. Then due to unit force. So if you want to find out what is the deflection at the point C, so what you have to do here? So you have to apply a unit force at the point C. You have to remove all the external forces. Remove all the external forces. Only have to consider the unit force at the point C, and due to this force, so you have to find out what is the deflection at the point C. So consider the simply supported beam shown in figure 5, subjected to a unit load acting at C. This is the unit load acting at C. Let moment small m at the section due to unit load at C. So due to this unit load, what is the moment at the section that you have to find out? What is the moment at the section that you have to find out? So let us take that moment is your small m. So due to unit force, the moment you take at the section, that is your equal to small m. You have to take the moment due to the unit force, that is small m. Then what is the stress produced in the element due to unit force? Due to unit force, what is the stress produced in the element? This is the element. So this is the this is the stress produced in the element. When the unit force is applied, you have to take the stress in the element, your sigma dash. And what is the stress produced in the element, that you have to find out at a distance y from the neutral axis. The stress produced in the element due to unit force is equal to sigma dash. Here also you can find out from the theory of pure bending, you know the formula. M by I is equal to sigma by y is equal to E by R. So sigma is equal to M by I into y. But in this case, so what is the stress produced in the element? This is your sigma dash. So sigma dash is equal to small m by I into y. So this is the bending moment at a section. This is the bending moment. The small m is the bending moment at a section due to the unit force. So what is the stress produced in the element at a distance y from the neutral axis? So at a distance y from the neutral axis, what is the stress produced in the element? That is equal to sigma dash. So sigma dash is equal to small m by I into y. But you know the deflection at point where unit load is applied. So already we have derived the expression of deflection at a point is equal to integration of sigma dash epsilon and dB. Here you take the deflection at point where unit load is applied is equal to delta is equal to integration of sigma dash epsilon and dB. But you know the stress produced in the element due to unit force is equal to sigma dash. So sigma dash is equal to small m by I into y. So here you take this is so here you put the sigma dash in this equation, and you know what is the strain also. The strain that you have to take from the external load system. The strain in the element due to given system of forces, you know, epsilon is equal to stress by modulus of elasticity is equal to the this is m by ei into y. M by ei into y. So this is the strain. So here you put the strain. Here you put the sigma dash and strain epsilon. So sigma dash is equal to m by I into y. So deflection at point where unit load is applied, delta is equal to integration of sigma dash epsilon dB. But you know sigma dash, the stress produced in the element due to unit force is equal to small m by I into y. And you know the epsilon, this is due to the external applied forces. So this is equal to m by I into y. So you put this sigma dash and epsilon in this equation, deflection formula. So small m by I into y into capital M by ei into y into dy. Then the delta is equal to 0 to L integration capital M small m by ei square, and here you take in bracket integration from 0 to a y square into dA, because this is the change in volume. So take the change in volume, change in area into change in length. The change in area and change in length is equal to the change in volume. So you split the change in volume to change in area and change in length. So here you take in bracket integration 0 to a y square dA into dx. But you know, integration from 0 to a y square dA is equal to the moment of inertia. You know, this is moment of inertia. Moment of inertia is equal to integration from 0 to a y square into dA. So here you put I is equal to this one. So substitute this by I. Delta is equal to 0 to L m capital M small m by EI square into I into dx. Here I cancel, then the delta is equal to integration 0 to L capital M small m by EI into dx. So this is the deflection formula. If you want to find out the deflection at a point, using this formula, you can find out what is the deflection at a point in beam or in frame. Capital M is the bending moment due to the external applied force, and small m is the bending moment due to the unit force. dE is the modulus of elasticity and I is the moment of inertia. So this is the formula. So the deflection of a beam by unit load method that you can find out, that is the deflection at a point, delta is equal to 0 to L capital M small m by EI into dx, where capital M is the bending moment due to external forces and small m is the bending moment or the section due to unit loading. E is the modulus of elasticity and I is the moment of inertia. So using this formula, you can find out what is the deflection at a point of a beam. And this formula is also applicable to rigid frame, where the flexural effect is only considered. This formula is also applicable to the rigid frame, where only the flexural effect is considered. There is no effect of axial and shear forces. Effect of axial and shear forces are neglected. Only you are considering the flexural effect. And by considering this flexural effect, you can find out what is the deflection at a point by using the unit load method. This is equal to delta is equal to 0 to L capital M into small m by EI into dx. So this is all about the expression or deflection of a structure. Now all are clear how to find out the deflection using the unit load method.